Hello everyone. So previously we had discussed on the tree DP algorithm or dynamic programming on the trees algo, right? So now we'll be discussing about the digit DP algorithm. Yeah. So let's see what the definition part say here, right? So let's get into the definition part. So here digit DP, also known as digit dynamic programming, is a dynamic programming technique used to count or calculate the values over the numbers within a range over a number within a range by processing their digits. Simple. Now let's hop into the next point. It helps solve problems like count numbers less than n that satisfy a certain property efficiently without iterating through every number. Without iterating through every number, this part of the sentence is very important. Yeah. So it helps. So this is nothing but the use case here. So I have just mentioned the use case. I found this one, what do we call, important. So I have just mentioned the use case here. It helps solve problems like count numbers less than n that satisfy a certain property efficiently without iterating through every number. So this is fine, I believe. Next, let's move on with the explanation part, right? So when you deal with the problems like count this one, when we are dealing with the problems like count how many numbers between 1 to n have a certain property, right? 1 to n have a certain property like having no repeated digits. Suppose if the digits are repeated, right? So we if we have to count a certain this one, what do we call, numbers without what do we call, having no repeated digits. So suppose if we have array of numbers 1 1 2 1, right? So 1 is repeated thrice here, right? So if you want to this one, what do we call, go with only the number which is not repeated here. In that case, we'll be making use of this algo. Yep, digit DP. So count how many numbers between 1 and n have a certain property like having no repeated digits. Having, you could naively or straightforwardly check every number up to n, but that's too slow for the this one large n, right? So if you are considering up to 10 to the power of 18, yeah, so that's very slow if you are checking every number, right? So digit DB works by breaking the number into digits and using the DP to remember this one results based on certain things. One is position, current digit that we are processing, position in the sense current digit that we are this one processing, or we have we are going with the current digit in simple terms. Yeah. Next one, tight constraint. When I say tight constraint, whether the current prefix is still equal to the prefix of n. Yeah, whether the current prefix is still equivalent to the prefix of n. Other state parameters like sum of digits, previous digits, etc. Right. So now let's go with the example problem for the code. Actually, we have to implement the algo for something, right? Algo on something. So let's consider the simple example here. So let's go with count how many numbers from 0 to n have the sum of digits less than or equal to k. Yeah, less than or equal to k. So we'll implement this one with a digit TP. Yeah, let's start writing the digit TP algo here. Right, so let me go with the function here, def count numbers. I'll just name this one with some limits. Yeah, with some limit, or I'll just go with the limit here. So I need the parameters. One is n and another one is k. 0 to n, we are considering less than or equal to k, right? So yeah, we are going with, we have to count how many numbers from 0 to n uh, that have the sum of digits less than or equal to k basically. So that is the reason I want the parameters n and k. Yep. Now let's convert the number to the list of digits for easy access, right? So I'll just go with here digits equals. So let me go with list of uh, map, list of map of, let me go with int, comma, string of n, string of n. So this is fine. Let me assign dp to this one. Yep. Now let's do one thing. Let's go with the recursive function for the dp. Let's go with the recursive function for the dp. So let me go with def dfs of position. I'll just go with a tight as well. Let me go with a current sum. Let me go with a current sum. Yeah. Now within this function, DFS function, let's go with a base case. Base case in the sense if we have processed all the digits, right? So I'll just consider here if position equals length of, let me go with digits. So this is fine. Yep, the next step would be what if the sum of digits is less than or equal to k? We have to count this particular number itself. Now, let me return something here. So I'll just return 1 if current sum is less than or equal to k. Else, let's go with 0. Yep. Now let's go with a memoization check. Let's go with a memoization check. Yeah. So let me go with key. Let me assign the key to position as well as type. Let me go with the current sum as well. Yeah. Current sum as well. So here if key in DP, if key in DP, then let's return here. Let's return dp of key. Then let's return dp of key, right? So otherwise, let's do one thing. We have to determine the max digit that we can place at this particular position, right? So let me make use of the keyword limit here. Let me go with digits. We have here within the suggestions. Let me pass the position as well pos keyword that we have considered variable name. If tight actually, if tight else, let's go with a 9. Let's go with a 9. So this is fine. Next, let's initialize the total to 0. Let's initialize the total to 0. Next, what shall we do? Let's try placing all the possible digits from 0 to the limit. Let's try placing all the possible digits from 0 to limit, right? So I'll just go with for D in range. So let me go with here 0 comma limit plus 1, right? I'll just go with limit plus 1. Yeah. So now let me go with if we place D, the next tight condition depends on whether D is equivalent to the limit or not. So I'll just go with new tight here. Let me assign this one to tight and D equals limit. Yeah. So this is fine, man. Yep. Now this is fine. Let's recurse for the next position. Yeah. So I'll just go with total equals total plus. Let me go with DFS of position plus 1. This is fine. Let me go with a new type. So this is also fine. Also, let me go with the current sum plus D. Yeah. So I'll just go with current sum plus D. Yep. So this is fine. Now let's do one thing. Let's store the result in the DP. Let's store the result in the DP. So this one DP of key. Let me assign this one to the total. Also, let's return something. Let me return here total. Yeah, let me return total. Yeah. Now this is fine. Let's start from the position 0. Also, let's set the tight equals true because we are bounded by the n initially, right? And also we have to set the sum initially to 0. Yeah. So let's return here. So this is fine, I believe. Is anything wrong here? 1 second. Yeah, let's do this. So I'll just go with the return DFS of 0 and right equals true. This is fine. As I've said, also initially sum is 0. Yep. So these things we are done with the algorithm part. Yeah. So let me consider the this one. Let's go with the example usage here, and let me give some random number 1, 2, 3 here. This is fine. And k, let me set this one to the let me consider capital K. K, let me consider 4 or 5. Let me consider 5 here. So also let's print something for the interactive purpose. So I'll just go with here count numbers with a sum limit. Yeah. So this one, the function name I'm calling here. So I have to pass n along with a k. I have to pass n along with a k. So why it is showing like this here? N and k itself we have to pass, right? Oh, this one capital N and capital K. So this is fine. Now, yeah. Now wait. Now this is fine, man. Yep. Now, let's this one. Let me go with the or let me explain this one entire all go before running the code. Actually, let me explain this one entirely. Then let's discuss the output. Or what is the output that we need to get? Why we have to get the output, and then let's run the code. Yeah. So let me explain this one very quickly. So digits equals list of map whatever I have made use of here. This one, line number 30. So we are just converting n into the list of digits for easy indexing here, right? So suppose example 1 to 3 we have considered, right? So that will be 1 comma 2 comma 3. That will be considered as 1 comma 2 comma 3. Yeah. So DP, this one, what we are doing here, we are just making use of the dictionary for the memoization. Yeah. Store already. So it stores already the computed states. Now we are going with the DFS, this one function. So this DFS function, we are going with the position, tight, as well as the current sum. So this is nothing but the recursive digit DP function. Yeah. So within this DFS function, so what we are doing, I'm just going with a position equals length of digits. So this one, if we processed all the digits, then we have to check if the sum is less than or equal to k accordingly with the algo that we have considered, algo that we have discussed, or accordingly with what we discussed in the explanation part. Yeah, that's what we are doing here. We have just articulated the same thing in the form of code. Yep. Now key equals position tight. So this one current sum, whatever I have written here. So this is nothing but we are just this one defining the DP state by position tight constraint in the current sum. We know this. Yeah. Now let me go with the limit equals digits of position. This one I have written. Yeah. If tight, else we are displaying 9, right? So if the tight, if it's tight, then we can't go beyond the current digit of n. Otherwise, we can just go up to 9. Else 9 we are given, right? So this is fine, I believe. Next, we are going with a for loop. Yeah. For d in the range 0 comma limit plus 1. This one. The line number 44 actually. Yeah, this one we are just trying all the possible digits at this particular position. Now we are going with a new tight, this one, line number 45. So tight remains true only if the current digit equals the upper limit. Yeah. So this is fine, I believe. Next, what we are doing, we are going with total equals total plus DFS of position plus 1, this one, along with the new tight and current sum plus D. So this one, actually, we are adding all the valid counts recursively. We are just adding all the counts recursively, right? Recursive DFS basically. Yeah, we are going with the recursive DFS in simple terms. Now, we are just saving the computed state to avoid the recalculations here by making use of DP of key, by assigning the DP of key to the total. Yep. Finally, we are going with the return DFS of 0 to 0, nothing but I had explained this one at the end. We are just starting the recursion with the first digit. Tight, we are setting initially that one to true, and sum will be initially 0. Yeah. So this is it for the all go. And this is nothing but the example part. This is nothing but the example usage. Yep. So we have considered n equals 1, 2, 3. K I have given 5. So what is the output that I need? What is the output that I need to get here? So 81. 81 is the output that I need to get, because there are 81 numbers that is less than or equal to 1, 2, 3, whose digit sum is less than or equal to 5, right? So see, here, this one, what do we call? We are counting numbers less than or equal to 1, 2, 3 with the digit sum less than or equal to 5, with the digit sum less than or equal to 5 here, right? Again, what we are doing, we are counting the numbers less than or equal to 1, 2, 3 with the digit sum less than or equal to 5. So suppose we have considered 0. 0 is nothing but sum equals 0 here, right? So this is fine. For the 5, for the 5, the sum equals 5. Yeah, sum equals 5. For the 15, sum equals 6. For the 15, 1 and 5, sum is equal to 6. 1 and 5, the sum is equal to 6. For this one, 104, for 0, we can just directly take 0. For 5, we'll directly take 5. For 1, 5, we will be going with 1 plus 5 actually. That leads to the sum 6 actually. This is fine. For 104, 1 plus 0 plus 4, that will lead to 5. Nothing but we'll be considering sum 5. So this one we cannot consider. Just for the example I'm showing, right? So we have to go with less than or equal to, until less than or equal to 123. Until less than or equal to 123. Yeah, total basically we have to get the 81. The all basically here I'm just showing this one for the example sake. That's it. So this one we have to consider. This one we have to consider because this one k we have considered up to 5. Okay, we have considered up to 5. Again, we are counting the numbers less than or equal to 123 with the digit sum less than or equal to 5, right? So we'll not be considering this one because 1, 5 will lead to the sum 6 and 6 is greater than 5. We shouldn't be considering this one. Yeah. So this one we cannot consider. So next we are going with a 104. Sum will lead to the 5. This one we can consider and so on, right? So this is the three numbers and so on. This one will be calculating further things as well, right? Further things. So total we have to get 81 numbers. 81 numbers less than or equal to 1, 2, 3. Less than or equal to 1, 2, 3, digit 1, 2, 3. We have to get 81 numbers that sums up to this one. What do we call? 5 actually. Yeah, that sums up to digit sum less than or equal to 5. Yeah, so this is fine. So I hope now it is clear. Now it is clear. If I run the code, I have to get the output 81. Let's check the same. So let me copy this one entirely. I'll just give Control J. Let me hit Python followed by the file name.py. Yep. So we are getting 33 here. Somewhere I have messed up something. Let's check what is wrong. So here actually for the type we are making use of the boolean, right? Boolean true. We are going with the 0, 1 and 0. We have made use of the integer actually. What if we give 1 here in this place? Instead of the true, we give 1. Do we get the correct output? Let's check the same here. Still we are getting 33 itself, right? So this one true, we are representing this one in the form of 1. This is fine. Somewhere we have done something wrong. Just give me a second here. So actually, whatever the output 33 we are getting is correct. Actually, we don't get 81. So there are not there are no 81 actually. There are 33 numbers which are less than or equal to 1, 2, 3. Yeah. So I got confused there. So only we have to get 33 itself. Yep. So whatever the code that we have written works correctly itself. So it is not wrong. So let me do one thing. I'll just paste all the numbers actually below or less than or equal to 1, 2, 3. That'll give the digit sum this one less than or equal to 5 actually. You can just check here. So let me comment this one. Comment this one. Yeah, these are the numbers actually 0, 1, 2, 3. So this one just for the sake of understanding. Yeah. So this just for the sake of reference or understanding. You can just go this one, go through this one. Yep. So yeah, 33 itself is the correct answer, not the 81. 81 numbers, there are no this one. No 81 numbers which are less than or equal to 1, 2, 3. Right? So that was wrong. 33 itself is the correct answer. Yeah, I got confused. So this is fine, I believe. Now we are done with the digit TP algorithm. Yeah. So again, this is it for the algo. So before hopping into the next algo, nothing but the bitmask DP. So let me summarize whatever we have learned so far. Right. So now what does the digit DP do here? So let me explain or let me summarize whatever we have learned so far. Just remember these 3 to 4 points, man. So what does the digit DP do here? Digit DP counts the numbers based on the digit properties, based on the digit properties. Yeah. So like whether it may be sum, whether it may be parity, whether it may be distinct digits, etc. without checking every number individually. So this is fine. Next, why we have to make use of the digit TP? So this one, this might arise. Yeah, I have mentioned the use cases, but why we have to make use of the digit TP? So there are other methods as well, right? So to find the sum, we can just count in other way as well, right? So means suppose if we have to count the non-repeated this one numbers within the array, we can do it in other ways which are faster than this. So see here, one thing. If you don't want to count the numbers again and again, go through the numbers again and again. So this will make use of the DP, as I have said, right? Digit DP uses dynamic programming, right? So that is one of the thing. So it drastically reduces the time from big of n to big of digits into constraints, right? It drastically reduces the time or the time complexity from big of n to big of digits actually, digits into constraints. So this is one of the biggest pros or the advantages of using this one, digit DP. Next, the third one is, what's the key idea here? We will be making use of the DP with the states. We will be making use of the DP with the states. Yeah. So this is very important. States in this case, so in every case actually, digit DP. So we will be going with the position as well as the date as well as the property. That's what we went with. Yeah. Position, date, nothing but that was related to the constraint. Next, finally, the property, right? I'll just write here prop, nothing but the property. So this is fine, I believe. Finally, when to use? So when to use this one, digit DP. So when a particular problem involves constraints that is related to the digits of numbers, whether it may be sum of numbers, even digits, uh, even digits count, or the palindromic digits, etc., then we can just go with a digit DB. Yeah, when a problem involves constraints constraints related to the related to the digits of numbers, related to the digits of numbers. So these are some of the points I found it very interesting and useful. So at any cost, you have to know these this one points, right? So I just wanted to discuss with you guys. So this is it for the digit DP algorithm. Yeah. Next, we will be discussing on the topic Bitmask DP. For now, this is it. Thanks for watching, guys.